All right, let's see. So what do we got so far? We got this here. All right, so again, this really, really, unbelievably makes sense. If you think about it, right? If he asked me to guess somebody's age, guess that guy's age, and I'll give you like $10. Like, well, how close do you need me to be? You need me to be exact? How close do you need me to be? How much error are you allowing me to have? So this is the guess. This is the best guess for something, is an average of a sample that I've taken. So the best guess for the average age at Grossmont would be, that we could probably get, is to take a sample of Grossmont students, find their average age, that'd be X bar, that's our best guess. And then we go up and down from that best guess, and we say that's the error that we allow ourselves within so much. Now what changes how big this error is? Several things. Can somebody give me one thing that would change how big that error is? I'm going to just look at the parts of it, and you can tell.
How many people's in your sample?
Yes, the sample size. The larger the sample size, what happens when I take a larger sample? How do I feel about everything I found out about the sample related to the population?
More confident.
More confident about it. Holy shit. So I should need less and less wiggle room then, right? So as n gets bigger, what happens to this piece? Well, it gets freaking smaller. Done it. I'm dividing by square root of n. Okay, I got what else? You can't change the standard deviation, right? You can't go, everybody suddenly be closer in age. No, you can't do that. That'd be really weird. Very specific X-Man thing. Is the z-score. What affects the z-score? What tells me the z-score for these kind of things? The amount of confidence that I want, right? Do I want to be 90% confident? Then I don't have to go out as much, right? If you want to be 99% confident, oh shit, you better cover your ass. All right, so you're 99% confident. If you want to be more confident you catch a fish, you got to throw out a bigger net, right? Okay, you guys kind of with me here a little tiny bit? Like this much? Okay. So an example of this would be, we did several before, but they have to give you everything. Let me change this up a little bit. And of course, I didn't bring my bag of calculators, but if I gave you a list of data, right, if I just gave you, I tell you that we know sigma is 3.19 for something. And we get this list of data, we take a sample of 6 things, right? Look at Jeff being all creative. 6 items. What are we measuring about these items? A characteristic. In the background, since it's only 6, what do we have to know about this to begin with? It's only 6. What better be true in the first place? I'm working with a normal distribution. I like it. Better be normal to begin with, because it's not a big enough sample to save its ass, right? So it's got to be normal. So let's say that, all right, let's try to make this something real. Let's say that we know that, what do you got, Jeff? Levels of toxin in this river has a standard deviation of this, right? We're downstream from some factor. You with me? So we know that. We know that from previous studies that have been done, we know that's there, and that's something that's within the amount of tolerance that the government lets happen, right? Because you all know that there's a certain amount of almost anything that they allow to just show up in your food. Or if you don't know that, then I don't know, look into it. We take 6 samples of the river, right? Take a sample of 6 randomly selected locations along this river, right? This is a decent problem, Jeff, I know. 6 locations. The river's toxicity, right? And we get this. We get level. Let's just make up some shit. So this is a level of toxicity. We get 11. We get a 9. We get a 2. We get a 7. We get a 3. What is that? 1, 2, 3, 4, 5. And we get an 8. I like it. Okay, so what is it that I need? We want to create a 99% confidence interval. Okay. So let's go step by step. Do we know what n is? What's n? 6. What's sigma? 3.19. What's z? Yeah, it comes from what? What do I get z from? Yeah, because z tells me how far away from the mean I am. So I need the z-scores that are far enough away that I catch 99% of the data. Let this make sense, please. Right, so how far out do I have to go? How do I figure out that z-score?
On the chart.
Oh, I want to point something out to you guys. Today we're going to get a different chart. Oh, yay. But it's actually going to make our life a little better in a certain way. I'll show you how. But you guys, I want you to notice something. We saw this earlier this semester. There's a little baby chart down here. A little baby chart down here. It said common critical values. But actually, if you look at it, it says confidence level. You see where it says confidence level down there? Common critical values. You see the little baby chart? Oh, so cute. There's a reaction. All right. How confident do we want to be in this case? 99%. Look, confidence level 0.99. What's the z-score? 575. Kick ass. I like it. I think we've done one like that before with the 99%. So my z, so 99% would have 0.005 out there, half of 1% outside, and you have to look it up, and you eventually get 2.575. Right, how's everybody doing? They've got to give you n. They've got to give you sigma at the moment. This is for section 8.1. They've got to give you sigma. They've got to tell you how confident they want you to be, so you can figure out what the z-score is. Now, what's the last thing I need for this formula to work? X bar. And I did a small enough one, you should be able to just do it. It's only 6 things. So how do I find the average of this? Add them up. 29, 40 divided by 6. I almost made it something nice. Oh well. 20 divided by 3, 6.67? We'll do 6.67. Is everybody with that? Everybody see that? They might give you a list of data. Ooh. So what do I have to calculate from that? X bar. You could do 1 var stats. Throw it into your list on your calculator. Do 1 var stats. It's a little tiny list. We can do that. Check. Are you guys still with me? So I don't teach it like this. I made you suffer through my explanation of where this thing came from. Do you guys remember that? If you were here, you're like, yeah, you do that kind of shit, Jeff. I know. But now that we have created this formula, here is a way you tackle a problem. What is it that I know, and what is it that I don't know, and how do I get what I don't know for this formula to work? Okay. So now X bar is 6.67. So now I got everything I need. 6.67, give or take, 2.575 times 3.19 divided by square root of 6, because that's what it is. So if anybody actually has their own calculator, I mean, it's so nice. I see several. Some of them are red. I like that. Anybody get the error? This piece. I like it. So 3.353. I like it. And now you just do 6.67 minus that, 6.67 plus that. I like it. So 6.67 minus 3.353. Hit second enter, you can just go back and make it a plus sign. So I get this little interval. I get 3.317 to 10.023. Can somebody give me 2 reasons why that's would you say that that's a decently wide interval? Yeah, I'd say it's a decently wide interval, right? Especially considering the size of the data points we got. It's a decently wide interval. Can you give me 2 reasons why it's so big? And what would make an interval big would be the error, right? Why is the error so big? Well, number one, we wanted to be 99% confident that our interval would catch a certain value. Then we got to make it big to be that confident. Secondly, right, small sample means I already was not that confident to begin with, so I got to make up for that. But mathematically, it makes the freaking error bigger when n is smaller. So I had those two things competing against me. So we're 99% confident that the toxicity level of this river is currently somewhere between 3.3 and 10. Right? It's like, oh, we better take a bigger sample, right? Something. Do you guys get that? All right. If the toxicity level was 2 before, is this evidence that something has changed? Oh shit, yeah, because is this consistent with 2? Does this allow for the mean to be 2? And again, understanding that in the background, what's the chances that we're wrong? What's the chances that our interval is in the wrong place? 1% chance, right? So yeah, given that there's a 1% chance that we're wrong, it doesn't look like it's the same as before. Something has changed, right? So this by itself actually would be enough evidence to show that something has gotten worse. Now notice evidence, not proof. Everybody confuses those two things, right? It's evidence, not proof. Why is it not proof? We just said there's a chance we're wrong. Shit. Like everything. That's why the whole reasonable doubt thing exists in the court system, because you can never prove to 100% degree. So it happens right there in front of the judge on TV and everybody's watching. Even then, maybe it was somebody wearing a mask. I don't know. All right. How do we feel about that? Is that all right? So sometimes some of these problems are just going to give you everything. Just going to give you everything. You just got to find the z-score. They're going to give you the mean. But sometimes they're going to give you a little list of data. You got to plug it into your calculator, figure x bar, and then throw it in the formula. Yes?
Can you go over the sentence thing over?
Yeah, okay. Let's see. Let me make a little room here. So we are, what? 99% confident. I like it. That.
The interval.
The interval. I like it. Assert that right word, I like it. Interval. That the interval, who to what to? I didn't give us any units, so 3.317 to units, whatever the units would be. Contains what? The true mean toxicity level of this river. I like it. And of course you would want to take various samples in various locations because toxins might pool in certain areas or whatever. Or there might be other sources of toxins somewhere. So you want to get kind of an average of the river. You want to get random locations. You like it? I like it. This is how they test almost anything, to be honest, right? This is how they test the stuff they make and box up cereal. They take a sample off the assembly line and see just how much rat poop is there in there. Oh, it's within the acceptable levels. Cool. Ship it out. Extra protein. Oh, I love the looks on their faces. You guys know this, right? I mean, there's a certain allowable level of things like that. Ooh, I like the looks. That's awesome. I've just turned people off to cereal. Yeah. Yes. It's all protein, people. Tell yourself that. Yummy, yummy. All right, just made your Frosted Flake experience that much more exciting. Okay, I can't. Some of you guys had to know this already, hopefully. Okay, so what we did last time was we took this and we converted it. We kind of started over again, but we had an idea of getting a percentage, a confidence interval for a percentage put together. So it kind of makes sense. If this is a confidence interval for a mean, I'm going to have a mean showing up. My best guess at the mean, give or take my allowable error, right? If I want to make a confidence interval for a percentage, there better be a freaking percentage here. So we figured out last time, we all did this together, we went through this crazy process. And we ended up with this freakiness. Trying to be a Q there. P hat, Q hat, over in. So this is my best guess for the percentage. This is what I get from a sample. This is the same old z-score as it was over there. It's based on the confidence level. This is acting as what? What's it in the place of?
Error.
No, this whole thing is error. What is this acting as? What's it in the place of in this formula here? Standard deviation. It's not squared, it's not variance. So this we'll come back later. When we need to make a z-score for p stuff, we're going to use this on the bottom as the standard deviation, because that's what that is. That is the standard deviation amongst percentages. Let me let that sink in. I'll bring it up again when we get there. How's that sound? Right now we don't have to know that. Okay. Somebody's like, why you told me that then? Oh, all right. Just laying groundwork. So let's do a quick example of this. And then we'll do the new stuff for today. Yay. Actually, let's do the one, if we didn't do this, we might as well do this one. Let's see if you guys can handle this. So number one, on the opposite side from the means, section 8.3, confidence intervals for proportion. Try to do what you can there. Anybody else still need a copy of that? All right. I love the people like 10 minutes in, they're like, can I get a copy of that thing that we were working on? Oh, yeah. Just to make sure everybody starts off on the right foot, how do you calculate p hat for this problem? X over n, sure, or what's that? I love you guys so much. How do you make a percentage ever? So what do you see in your sample? What do we see in our sample? We talked to 652 registered voters, and 459 of them voted. So what's the percentage? What's p hat? Would it be what divided by what? Yeah, 459 divided by 652. Cool. I like it. 704. Is that what you guys got? Remember, this is always at least 3 places. And remember, if you forget how to round anything, just go to 4 places you're covered. You got your ass completely covered then. So you should be able to finish that problem.